Today I just finished the matrix multiplication video and I want to continue. I've been doing I've taken a break to think about what to do next, and I've gone ahead and integrated the new matrix multiplication kernel into the ML library, and I've tried running it. By it, I mean this performance thing. This is the file that we're using to test the Leduc training loop. It kind of looks like this. We worked on that a few videos ago, and the goal is to try to optimize this. The results from a few videos ago were basically this. We had this duration of 81 milliseconds, yes. And of course, the compute and memory throughput were pretty low, and the registers were way out of hand. Today, after I integrated the new matrix multiplication kernel, I put it in, and the compute and the memory throughput is even worse, and the registers are still at 255, but the duration did go down from 80 to 70 milliseconds. But even though the registers are 255, I looked into the source and I couldn't see any memory leaks. If you look at this matrix multiplication kernel, wait, where are the live registers? Okay, now we can see the live registers. And we know from the previous video that this kernel only uses 136 of them. So, we can go through all of these and see whether something weird is going on. Like, does it exceed the limit that we expect? And it only really goes up to 130 or so. It's not like the last time where we got 250. Let's see. It's 200 instructions long. 2000, sorry about that. Yeah, this is the end of the kernel. It's restoring the data that it backed up in local memory, and yeah, this is it. And I looked at the other kernels, like this is the kernel for the neural network loop itself, for the neural network model itself, and it doesn't go it doesn't go up much. And we know that when we remove the neural network model and all the other stuff related to it entirely, and only use the random players, that the game itself only used about 120 registers. So I did go through this entire thing. And take a look at the live registers. You'll see that they don't go about 120, maybe 125. We can see them here or there, but yeah. Okay, here it is, 120. Permute. Is this maybe for the permute register pair? Oh, really? Does that mean it simply swaps them? I don't know what this instruction is for, but never mind. Okay, it's briefly on this call. It's 234 live registers, but otherwise in the kernel itself, it doesn't seem like it goes about 120, and that makes sense from what we know about how this kernel should behave with two random players. Yeah, okay. So what I've tried doing to optimize it next is to get rid of these no inline functions. What I've done is gone into the for example, the layers. Previously we had a let here, which would put a join point over the body. And I changed that to an inline. And I also changed this let to inline. And now that it's inlining everything, once we run that, what we get is this performance. The duration goes down to 60, but of course, it seems like the compute and the memory throughput haven't moved at all. So I think we cannot really trust the profiler too much when it comes to performance. We can only trust the duration. The number of registers is still very high because the reason for that is probably because it's reusing the registers for the machine learning library. Like the game is 120 and the machine learning library is 130, so it maxes them out in the end. And I've been wondering what can I do to improve this. Okay, I did get two ideas. One is really easy to try out. We have this backing up that we are doing. Let's see. No inline train. Well, it's probably in the loop. Yeah, we have this transposing loop backup. And I realized that when I looked into the no inline functions, I realized that they automatically back up the data inside the registers automatically. That was actually when I realized how functions could work in CUDA, even though it doesn't have a stack. It just backs up the values in local memory. And that made me realize that we don't really need this. Oh, wait, what's going on? Yeah, we'll do it like this. Okay, let's remove the table. We'll assume that the compiler is good enough to back up everything on its own. Yeah, and let's try this optimization to see if it makes things any better. Maybe it will make things worse. I don't know. Previously, it was backing things up in shared memory. And now it should be, I don't know, maybe it'll back them up in the cache, who knows. We'll let the compiler itself decide. Yeah, also compared to the previous videos, what I've done is started backing up the old reports so we can go back to them more easily. I have to press Ctrl C when it refuses to exit automatically. Oh, it actually got worse. Interesting. The number of registers it uses is 248. Oh, really? Okay, let me try doing it once more. Maybe we'll do it a few times, just so I can make sure. I'm kind of surprised that actually backing this up did make things better. For once, one of my optimizations did bear fruit. It kind of keeps getting worse, actually. Let's try it one more time. Oh yeah, I'm quite amazed. It seems like that optimization did in fact may make things better, even though it increased the register usage. We're going to undo this. Yeah, I did spend a lot of time thinking about how this could be optimized, and I'm glad that it actually worked. So let me think. Let me just see how this is implemented, because I forgot what this was doing. It takes in a reference and backs it up inside it. Okay. A state. So we have this state backup table reference. Okay, so what's that? Community card is button first. Wait, what's inside the state? The state is a mutable heap variable. It has the backup table. Oh, okay. I understand. Okay, so honestly, it's actually pretty unfortunate that this optimization is working, because for this video, what I wanted to do next is try replacing this state from being a heap mutable variable to being a stack reference. This is very similar to what we had in the original training loop, where we were passing in a bunch of stack references. But what I wanted to do is implement a new layout type for the language, so we can just replace this mute with a stack ref. In that case, once we do that, this backing up the table like this won't really make sense. So let me just try running this one more time, and then we're going to do it, because right now my goal is to optimize all of this. And if you look here, like on the bottom, it keeps complaining about uncoalesced global accesses, and these aren't the ones from the matrix multiplication kernel. These are due to the fact that we are allocating that state on the heap, and every thread is, when it tries accessing the addresses, they are definitely uncoalesced. I did that to reduce the register pressure. So, and now I'm wondering whether getting rid of that optimization would make things better. Now that we've lowered now that we optimize the matrix multiplication, so the registers aren't getting in the way. By the way, we've optimized the matrix multiplication from 170 milliseconds to 80. But it only really reduced the runtime of this training loop by 10 milliseconds, from 80 to 70. So even if we optimized it a lot more, so it's as fast as the Cutlass kernel, we'd only at most get 5 milliseconds of improved performance. Maybe if we used a lot larger models, the improvement would be more pronounced, but right now that's not the case. Oh wait, what is this happening? Oh yeah, the register is 255, the duration is 68. Okay, let's try it a few more times. I'm confused how this works. Because I got 60 and I was really happy, but now I see that the performance is bad. I'm wondering whether this screencast that I'm doing is maybe doing something to impact the performance poorly. Uh, I have no idea. Right now, we pretty much lost all the improvement that came from inlining everything. Let me pause here for a bit so I can try running this without the screen recording being done. It's probably stressing the GPU a little. Okay, I ran it a few times. I forgot exactly. Yeah. Okay, let's see. This is. Oh yeah, this is the one with the backups that worked really very well. It's it was in hindsight the best run ever. Now this is when we remove the backups. You can see that we have 248 registers. But this is what we got when we ran it with backups again. The duration was back to 68. Now this is with the backups again, 64, 66, 65. And this is without backups. I managed to get this 62.21, which is actually pretty close to 60.83. So I think I might be getting fooled by randomness. When I got to this, I thought, wow, I guess the backup and the no backup versions are the same after all. I'm just getting fooled by randomness. And then I ran it again. I got 77, which is pretty much the worst run ever. I don't understand it at all. And here you can see me running this again and again. And they generally are below 70. So I think, here I got the 62.32 again. So I think, in fact, that we aren't getting any benefit from doing the backups. We don't need this after all. Which is, this is, it's not helping either way. The compiler is good enough to back things up on its own. And in fact, in this version, when we had this, when we didn't have this commented out, it was using more registers than without it. But the whole reason why we are backing things up here is so we can actually save the registers, and here it's using them up. So we don't need this backup. It's going against its intended purpose anyway. So, and it's it's just making the code base more complex. So yeah, we'll go with this version. Let me just do a note. Yeah, in fact, we can just get rid of this. We can. Yeah, I think I'll also remove this. I actually opened a bug regarding this because it's not. Because the reason why I didn't use this, why I didn't use the static global memory is simply because it wouldn't construct the union type in static global memory. It was basically complaining that the static initializers wasn't working. even though it would in a regular C++ compiler. So I opened a bug report with NVIDIA for that. Okay, so we don't need that. We're going to get rid of that backup table. It's simply a complication that we don't need. Where is it? Init game. Where is the state? Yeah, okay, so here it is. Backup table none. Perfect. Now let's try running this again. Maybe we'll get a little better performance now that we've gotten rid of the of that backup table in the global memory. The elements in the global memory should be closer together. We'll see. It takes around 15 seconds to compile this kernel, which is actually a lot better than for the game itself. For the game itself, because of all the serialization code, it takes very long time to compile. It takes nearly a minute. It was crazy. Okay, I shut this down. We're getting 68, 348. So yeah, it's roughly the same thing. We didn't see any difference from reducing the global memory footprint. Back when we started optimizing this, as I mentioned, we had all of this data in on the stack and in local memory. So that means since GPU doesn't have a stack, instead it has a register and it has registers and the local memory. That means it was stored there. That's what I mean when I say stack in the context of device kernels. In the context of GPU device kernels. Let's see how much we got. 71, whatever. And actually converting the code so it uses this this layout type in global memory did make the performance worse. Like I only really tested it on a random player. That's the only place where I really saw a difference. When I was just running a random player versus a random player. And previously we got something like 400 microseconds. And after we started storing the data in the global memory using this heap mutable type, the performance actually got a lot worse, from 400 microseconds to 4 milliseconds. Of course, that didn't really bother me too much, because once we added the ML library, the runtime went to 70 milliseconds. So I'm not really bothered about using the global memory thing, but it's still a blemish on all of this. And I don't know. I'm just curious about how good the duration will be if we went back to what we had before. And the thing is, I don't want to convert everything to how it was in the training loop manually. Instead, I simply want to have something like a stack-based layout type, so I can change mute to stack ref and have it be allocated as a reference on the stack. And that is what's going to be the subject of this video. We are going to add a new language feature to Spiral, similar to this too. We can start with the partial evaluator. It's no problem. I wish I could just copy this to heap stack mutable. Okay, let's do stack mutable. We'll call it stack mute. We'll add a new language op here. Wait. And we're going to add a new layout type. Stack mutable. Uh-huh. Hmm. I guess we have these special. I wish we had simply tie layout to. I wish we had something like tie to layout, but we don't. In fact, we can change the code generators. It's not a problem. Since now we have a tree, it's going to be kind of messy to have tie to, and we're just going to put a layout here. We're going to pretty much have to change all the code generators. Heap. Heap mutable. Mutable. Wait, it's supposed to be stack mutable. And of course, we have a bunch of things. Layout index. Now, yeah, we have all these. We're going to have a bunch of missing cases, and we'll have to go through all of them in order to actually make this work. Okay, let's fix the type errors. Tie to layout. Yes. Over here we'll go all the way back into the infer module, and we're going to add stack ref as a type, or rather stack mute. Stack mutable. Oh, that's all we need to do here. Wait, it isn't. It seems like. Yeah. Okay. Stack mutable. Yeah, it's really great how now we have inexhaustive pattern matching cases. We can just follow what the compiler is telling us and fix everything. Stack mute. Yeah, I mean we shouldn't have anything here. What about the prepass? Yeah, it doesn't have any particular functionality for mutable types. The partial evaluator does. So yeah, as you can see, it's very easy to add some features to the language. Now let's see. Yeah, it's complaining about this. Stack mutable. I mean, I think all three of these should be rewrite, because I'm not sure whether for heap allocated types I want the compiler to substitute them if they are the same, if they have the same data. I probably want them to be the same reference. Who knows? I mean, okay, let's change some things. This is going to be a new minor version of Spiral anyway. Now I still have one case here. So let's think. Oh yeah, it's basically the reason why we're doing this like so. Because we have indexing by key, and really in the heap mutable we don't really like index. Wait, what's the key here? Where is the key coming from? So yeah, here we aren't using the tie index all. Yeah, but yeah, the reason for that is where we are when we're indexing into a normal layout type, we're doing indexing by the individual keys, and that gives the chance to the compiler to apply common subexpression elimination. So if we index into an immutable type once, and then you index into it again, it shouldn't need to do two accesses in global memory. It will just get what's already on the stack. It's a little optimization that I did here. Even though since I made Spiral V2, I never really used the layout types much. The microphone is working, thank God. I mean, I'm finally doing some real work on the language, and I don't want it to be a repeat of the GADT video where I spoke for like a week into a non-working microphone. So now I think we're mostly done. We just need to add the missing cases to the code generators, and for all of the code generators apart. Title layout, and this is going to be heap. That's all we need to do here. I am not going to implement support for stack references in the F# code generator. Raise code error. The F# backend doesn't support stack mutable types, layout types. Maybe I should have named them something less confusing than layout types, but I don't know why I was so insistent on naming them layout types, because layout doesn't really refer to an object, but to a property of an object. But I guess if we actually think about it, the heap and the mute and now the stack mutable, those are referring to a property of the type they are that they have. Okay, now where is that? Okay. This is going to be heap. Oh, this is going to be, yeah, mute. And this is going to be stack. I'm really going to copy the error from the F# backend. We'll just do this, put it here. The C backend doesn't support stack mutable layout types. Oh yeah, we still have the missing cases here. I forgot about this. I also forgot it in the F# backend. Can I close all to the right? Oh, whatever. I can close the other tabs. For fuck's sake, this. Stack mutable. I think we're going to have to factor this out now. We cannot do this as a one-liner anymore. Indexing into what's the problem? Match lay with wait, this is already a match statement. I mean, just put it here. What the hell? Fun X. Yeah, I keep forgetting that this isn't Visual Studio Code. Yeah, I have a cold. Yeah, I mean, when you get older, nothing's going right. Wait, we have an error here. Aha. So that's why we were destructuring. Okay, so I guess it's going to be a little bit of work like this. And now we have to do the same thing in the C backend. I'm going to pause and fill in these cases myself. So because I don't want to bore you with this, and I think once we're done, we have to index. Here we have the index. We have all that. Yeah. Okay. Let me pause here. Here it is in the C backend. We'll have to do the same. We'll do the same thing in the Python backend. Let me pause here. Okay, I just realized something. Did we take care of the layout heap immutable set? Oh, let's go back to the partial evaluator. We'll go back to the code generator a bit later. Heap immutable set. Oh yeah, we're going to have to add a node, something like e layout set. Layout set layout. Oh yeah, now that I think about it, we're also going to have to modify the type inferencer so it infers the correct type when setting. Block parsing layout. Actually, this is going to be a bit more complicated than I give it credit for, and I'm not even sure whether this will really improve the kernel that we are working on. We're just generalizing this particular case. Oh wait, do we need the layout? Oh yeah, we don't need the layout because we can just get the layout based on this thing here. Like we'll just check the variable that we are indexing into, and if they are keep mutable or stack mutable, then it's fine. Otherwise, it's not. Okay, let me leave a type error here. It's going to be easy to do this in the partial evaluator. Where it's going to be hard is to actually do it in the type inferencer. Oh damn. Actually, this is doing it in the type inferencer is the hardest part. I didn't think about this at all. Okay, now where is the case? It's somewhere in infer pattern box. I mean, here it is. Raw heap immutable set. It has its own special. Okay, I'm not going to bother trying to change all this. So it first checks whether type variable is of the correct type. I mean, that would actually be the cleanest way of doing it. Okay, while I think about this, let me make a brief digression. We actually, back in 2018, the old spiral did have stack layout types. And arguably back then they weren't actually immutable, but immutable stack types. And in the old spiral, the layout types were quite different from what we have now. The layout types that we have in the current version of spiral only have the types themselves. But back then they were called reified join points. And they could even capture variables, literals, and pretty much everything else. There is no real analog to this in the top-down segment. It's impossible to type, I think. No, I mean, if you... Yeah, you could only type it maybe as a generic type of variable, and no other way. So I guess now you can maybe replicate half of what those reified join points were capable of using layout types, existentials, and type literals. That's one way of doing it. You still wouldn't be able to capture type aliasing. I mean, not type aliasing, but variable aliasing, like in regular join points. You know, if you pass in two variables that are the same into a join point, it only, when you look at the generated code, it only generates code for a single variable. That's how it worked in reified join points. And yeah, we're going to have to end up modifying the parser. No, we won't. I guess we're just going to modify this so it takes a look at this hating. I mean, it's going to be a type variable, this hating. Wait, what's this v thing? So this is a type variable. Yeah, here it's trying to unify it. So, okay, let me just maybe sketch it out briefly. We could do like this. And this will try to infer the type of A. And now we can go into match, let's say, visit T V with if it's something like a tile layout, or stack mutable, oh, then it's okay. Let's indent this. We can do it like this. Oh, wait, I erased the arrow. So what's the problem? Maybe it needs to be like this. Oh yeah, like that. And if it's something else, like for example, heap, then we do a type error, a raise type error exception, I guess this is how we're doing it here. Expected mutable layout. And we don't have this, so we're going to add it. Wait, what did I do? Oh, okay. Wait, this is a record, not... I should have just duplicated something like this. It even has a type, great. Expected... okay. Sorry about that, I'm not reading at all, but I'm copy-pasting, so I'm acting like a robot. Yeah, great, now we have this case. Wait, let's not... this is... Let's do as v, because this is the v after it has visited it. What's the problem now? Yeah, so it can be pretty much anything else, not just another layout type. Yeah, what am I thinking? And here we have this... Oh yeah, we have to put it at the end, otherwise this case below it won't be matched. Oh, not bad. And now we'll have a missing case, like over here. I'm just looking at the sidebar. When you have this green thing here, it indicates an inexhaustive pattern matching case. I kind of miss the keyboard shortcuts from Visual Studio Code, but otherwise I like the Visual Studio ID. You kind of get used to just using cut and paste and copy paste instead. It's kind of rough after, because the Visual Studio Code it has such great and sensible defaults, but this doesn't. Mutable layout. Mutable layout type. Got what? Does this take in? Yeah, it takes in a type. Okay, great. Yeah, now we'll be getting a type error. The only problem is that it won't be... that it won't be unifying the stuff. If you have something like... let me do it somewhere else. Like... In Spiral, if you have something like X, then right now it will automatically infer that this should be a mutable layout type, because that's what this operator applies to. But after this change, that won't be the case anymore. It will be expecting expecting an annotation. So let's actually improve the error message a bit. Layout set must be annotated. I think, yeah, in Spiral, I think you can have a mutable type without necessarily any records to index into. Like in F sharp, let's try it out. In F sharp, you have only you only have a mutable record, and in Spiral you can do something like let's see, QA mute int mute 1 2, and then QA 3 4, and this type checks. And if I oh yeah, we cannot put in an underscore here because the layout types aren't nominals. Using these deferred annotations only works on nominals. So okay, I suppose we did it like this, like I32, whatever. Yeah, now it will automatically infer that this is a mutable type. Let me just put it here, foo. We'll make this a test, a language test later. Now this basically works, and once we compile this, it will stop working. Of course, we'll have to modify the code generators and everything else. And the way to fix it will be to just put in the annotations everywhere. And this will be a new minor version of Spiral, I think. So it might be a meaningless minor version. Okay, let's see. Layout set must be annotated. The variable being set in must be annotated. The layout type okay, let's just yeah, this is fine as a type error message. So we'll also, like, when you do a fresh variable, it will be a time metamor. And because we're doing a visit, we know that this meta variable isn't annotated. You can have meta variables, but they could be pointing to some other type. And by calling this visit, we back up the tree of we back up the tree to the final value that the meta variable points to instead of the meta variable itself. So if we have this tree, if we have this here, we can be sure that it's not annotated. Layout set must be annotated. Okay, perfect. And instead of row heap mutable set, we'll have what? Row okay, row mutable set. Oops. Instead of doing this, I should have just renamed it. Let me do that. We'll undo all of this. Raw, mutable. Oh wait, this is not in this, but in probably in block parsing. Oh yeah, it's here. Okay, now we'll press Control RR. Let me just save everything before we try doing that, because sometimes the ID can crash. And now that we've done this, it will automatically rename all of these references, even in pattern matching cases. As you can see, we have where is it? Raw, mutable. Yeah, we have the raw mutable set everywhere, and I like that. I'm just wondering how raw expression list be. Yeah, I guess it's taking the symbols as expressions. I wonder if we have. Yeah, I mean, we don't have anything except the tie symbol. I think I'm not sure whether we have the splicing patterns in mutual in mutable layout typesets. We don't right now. Maybe I left this as raw expression list instead of a string list because I might have thought that it will be good to add in the future. Anyway, this expression is something we get from the parser, so we don't have to worry about this a variable being anything but an actual variable. Maybe it could also be an expression. Let me just if I do like QA. Oh, it doesn't parse. Yeah, I guess it does need to be a variable. It doesn't even parse this. This operator isn't parsed like the other operators are. Okay, so that takes care of that. The set operator is special. It has a special support in the inferencer. The reason why it needs that is simply because otherwise, if we did imagine this QEAA was something like a record and we did X or something like this, then it would end up evaluating the left side first, and we couldn't get to these. So we do need the special behavior for it. So let me think. Yeah, we have to go forward. Right now we are in the inference module. Let's see, the prepass. Uh, yeah, we changed this. We should have also renamed this. Instead of heap mutable, we have immutable. What do you do in the partial evaluator? Yeah, it should be a layout set. Uh, let me undo what we did in here. Immutable sit. Now, do we have any type errors somewhere, like in the pre-pass? Yeah, we don't. So what we're going to do is just rename this to, it should be like where? I'm going to press Ctrl RR and then rename this to immutable set. Yeah, perfect. And now it should be like this in the partial evaluator, and it is. Stack mutable. Oh, not bad. Not bad. Now I'm just wondering, do we need this layout type anywhere? Oh, we are actually stripping it away, it seems. Tile layout, mutable set. The fact that we are actually stripping the type from this variable might be a problem. But I think we can deal with it. Yeah, it doesn't have to be a heap mutable. I mean, do we need to check which type it is in the code generator? I don't think we do. We can code generate it properly. Regardless. We did this in the partial evaluator. I see that we have incomplete pattern matching case. Stack mutable. Okay, good. Now we can go back to the F# code generator. Heap mutable, stack mutable. Let me think. Do we need anything here? I mean, this one doesn't support the stack mutable types, and so yeah, I was still working on this on this code generator when I realized that I needed to modify the type inferencer. So I'm going to pause again and just fill out the missing cases. And we're going to resume when it's time to actually implement the stack mutable types in the CUDA code generator. Be right back. Okay, I finally did this, and now we only have the CUDA code generator left. Let's do it. Okay, I'll pause here so I can do these easy things. And immediately we have an issue. And this is actually where we need to start implementing new functionality. We're going to start by copy pasting this, and then we just do stack mutable. This doesn't exist, so it's going to be stack mut here. We'll have to create a new type for this. And for tile layout index all, yeah, it's going to have to have a base. We're probably going to just base it on the existing layout types. I mean, of course we are. It's going to be passed around as a reference type. And using that reference type, we'll just yeah, maybe do we make it a reference type itself, or will it be a data structure that has a reference and it's always initialized? We'll see. So let's see. Okay, we'll forget this for now. Now, what's this? We have something. Oh yeah, this is where where these cases are. Raise. You can just do raise congen error. It doesn't have to be a failed. And this is this is very similar to how it is in the other cases. X. I want to do this. This also has the stack mutable, and we need to put in a pipe operator. And yes, this is perfect. Now, yeah, this is layout track. Okay. Oh yeah, we also need to do this here. I just post forbidden so I can do this. And I think we have pretty much everything except these two cases. We have to implement the stack mutable, and then we are done with the code generator. Back when I was working on my first CUDA code generator, it was very difficult for me to actually figure out how to print out the types. I implemented it, and then I had a problem that the types weren't getting printed in lexical order. So I did some ugly hack with a stack inside the code generator to make it happen. But over here, we have a very elegant solution to that problem. It's honestly amazing. These are actually mutually recursive objects rather than functions. The reason why it's done like that is so this layout type can initialize the dictionaries. This will be stack mutable. Stack mut. Yeah, it forward declares it. These have a reference count. I don't think we need that. I mean, yeah, they don't need the ref count because they're not going to be put in share pointer. But that being said, how exactly are we printing these? Let's put in a bookmark here. And then we'll check out why layout. Oh yeah, here we have them. Stack mutable. It's going to be like stack. Yeah, they're going to be like this. And I think we'll make them references. Okay, I'm kind of not sure whether I want to make the type itself a reference like this, or whether I want to make its base a reference. We're going to try this out and see if it works. Oh wait, what the hell am I doing here? Okay, I see. So yeah, we can construct them like this. Oh yeah, as the ground value types, and unfortunately that will the reference will end up being. I mean, the reference would end up being declared and initialized anyway, and then we'd get an error during compilation. It seems that it seems like we're going to have to move this into tilet. Oh. Okay, let me pause here so I can think about it. Sorry about this. Okay, I've decided. We're simply going to make this type error during code generation. Raise code gen error. It will be a compiler error. It will be stack mutable types are references and shouldn't be returned. From join points or from, let's say, branching expressions. Like, okay, I'm not sure how to actually describe this as a one thing. Like, they're branching expressions, but they're like, yeah, from join points and if statements. I mean, is there anything else? Yeah, there's no problem with doing this. They're just, yeah, from if statements and you just get an error on the CUDA side anyway. And we're also going to make a special case for this in the code generator like here, and it's going to be tie layout, tie to layout, AB, stack mutable. And let's suppose we have this. We shouldn't declare the variables. That's why we put this here. Let's see. How are we doing this? Yeah, so we have things like array literals. And we take care of them here. Let's just put a bookmark here. I'm kind of curious about how we're handling this elsewhere. Like, but doesn't it say that this is compatible with the tail call optimization? Hmm. Okay, I see. I mean, yeah, okay, this makes sense. Even though, will this really work properly in the C backend? This TCO compatibility is that's when I worked on that there, and I needed to do that because if we just return something like an array literal, it might not increment the reference count. This is not like in C++. In C, you have to do it. You have to generate all the code for that and have it do it manually. In C++, we have that the thing which they call rei, and that's basically relying on the lexical scope to do all the allocations and to call the constructors and the destructors automatically. I don't like that because it ends up messing with the tail call optimization. Okay, we won't worry too much about that. I mean, if it isn't here, then it will just raise a codegen error. So let's get back on track. We'll use this as a reference, area literal. Let's just put it here. We'll comment it out. So we need wait, this is the type. Let me just take a look at the partial evaluator. Do we actually have the type? Oh, yeah, we do. We have this. Wait, no, we don't. This is the type of the data. Okay, I see. Mm. Wait, take a look at what we're doing here. Here we have stack mutable, here we have heap mutable. This is a mistake. I'm going to do a thing here. I don't usually do this, but we should do it right here. We should make use of this technique. We're going to fix it like this. Let layout equals, then we'll match on this as layout. Okay, let's do. I mean, I think we also have the op somewhere. Okay, let's make it op as op, and then we'll do a match op with the layout to heap. And yeah, this is going to be a raise type error. Forgot a case in layout 2. And now we just do this. We have to match on the op twice basically, but this does give us a code reuse, and I like that. Now we don't have to worry about forgetting to pass in the same layout. I mean, it was fine to duplicate it, like, you know, five lines twice, but now that it's 3 times, that becomes bad code. So thankfully we fixed that. We won't have to chase this bug in the code generator itself. So this is the type of the data. This is the stack mutable. And okay, so I mean, let's just do this. What's this? This is the annotation that this will be a string. We're going to declare this. Yeah, this has to be on the left side. And this part needs to be on the right side. Wait, this has... wait, I get it. This is 3 opening braces, and why is it closing so many? Okay, this is confusing me. Let me put a bookmark here. Okay, this can remain. Let me just like very title layout. It wasn't here. So yeah, so this is the closing brace for the share pointer. We don't have that here, right? Okay. I guess we can just do line S and then true. So, we also need the, let's see, array literal. Where is it getting the, so it's matching on this. Huh. Uh, why layout? I mean, it doesn't have to do the checking here, but we'll do it. It should rather be checked in the code generator. Expected. Stack mutable. Oh, this is for regular arrays. Of course, it isn't a reference here. It will just be treated as that when we do the type printing. We don't need this. So we have the stack mute. Oh yeah. Oh, this is perfect. Yeah, this is it should work if we do this. Oh, let me just remove this gap here. Now we can print this as a reference. So yeah, the reason why it's accessing the base is because it's getting the stuff is at the share pointer. We shouldn't be doing that here, right? Oh, okay. I think I understand this. So wait. So when it does the indexing, how is it doing that? Oh yeah. So it's doing it like that. I think we need a special layout index for stack. Okay, we'll rename this as into layout index. What heap stack. Wait, what's this thing? Yeah, this is the variable. It doesn't have to access the base. Oh yeah, so this is so this goes. It's indexing it. So the base is the pointer, right, and yeah, we'll be accessing it directly like this. I get it. Oh, oh crap! No, this isn't correct anymore. Okay, so we're going to have to pass the layout type into this function. Layout match layout with, and okay, so we have the heap mutable, and we have the stack mutable. We're just going to put this here. Great. Of course, now we're going to have to pass in the layout type. It's just going to be a lay. And I keep writing this shit out. Instead of doing this, I should put this into a function. Yeah, what the hell am I thinking? Get layout rec lay a, and this is going to be simply this. Why is this not used? I mean, I guess it's an editor issue. Well, let's deal with this. Play A. Oh yeah, this is. Yeah, I've been copy pasting that fucking thing instead of factoring it out into a function. I'm going to have to go back and fix all the other code generators. I'll leave that for later. For now, let's focus on this. We have this. We have the indexing. What about the setting? Tile layout set. Is it mutable set maybe? Set. Okay. Here it is. Tile layout mutable set. Okay, I see. String list data. Is it stripping the type from the variable? That's the one thing that I'm wondering about. I think, let's see. Yeah, it's fucking doing that. Instead of passing in the entire layout type, we're instead changing the type here for no real reason. Why are we doing that? I mean, we're only using that here. Yeah, this is very uncharacteristic. I for some reason decided to strip the type, and I cannot remember why I did it. I guess we're going to find that out once we remove this. Yeah. So Yeah, where are we using a tie? Yeah, I think because we're pattern matching on this. This is okay. I get it. Okay, suppose we didn't use this. Like, let's not do this here. We're just going to return a, and now it no longer has an a tie. And we also so like this, we can do. So we can do it like this. We just have to make sure that we're passing the same thing everywhere. And then, yeah, now this is bound here. For some reason, my mouse is messed up. Yeah, this should be fine. It's complaining about that here. Okay, great. Data to tie C. Where's the C tie coming from? So that's the yeah. So that's the type of the data. Okay, I see. I mean, what the hell? We're not even comparing the same thing. Like this is the inner type of the C. I mean, this is the type that we get when we take A and apply do all the record indexing with the strings. So yeah, this error is basically wrong to begin with. Let C tie. We'll just name this C type quote, and then there's a C tie, and C tie quote. Yeah, this is what it got unexpected. Okay, I probably never triggered this error once, so that's why I didn't see the problem with this. Okay, good. I don't think any of the code generators are using the inner type inappropriately in this immutable set. I mean, in this immutable set node. Let's see. Is this getting... yeah, this is getting used. In mute. And and in layout. And this is yeah, it gets passed in a type, and this gets passed into a dictionary. The only question is whether this is structural and reference. So it's a structural and nested with a reference. The reason why I do it like that is as a potential speed optimization that I've admittedly never tested. First, it tests reference dictionary for whether the value is in it, and then it does a structural comparison. That's how these dictionaries work. Yeah, okay. I like this. Uh, it won't cause us, changing the types shouldn't cause us any issues. So, okay, let's see. We're going to match T with Y layout. The inner thing doesn't matter, and this is going to be heap mutable. And we're also going to have a stack mutable. And this one is simply going to get assigned to like this. Now we're doing type checking in the code generator, but whatever. Where it turns out, as I keep working on the language, the code generators just keep getting more and more complex. They're doing a lot of stuff which should be a part of the partial evaluator, but whatever. Not bad. And everything that's triggered like this with a compiler error, that's a language error. So if you ever run into this, then open an issue on this Spiral repo and we'll fix it right away. It should never happen as a result of user code. Oh, great. So yeah, this is how we're doing the setting. And I think this is actually it. I can't think of anything else. Yeah, this is just a regular structure. And wait, did I remove the reference count? I think I did. That's not good. Let me just open this. Yeah, I'll go to the end. I guess I meant to... Yeah, I guess I meant to do it like... where exactly was it? I guess it was exactly there. Okay. So yeah, this reference count is at the start, no problem. So we are going to, I guess, let's do is heap. This field will be true, false. If is heap, then oh yeah, this is it. So I think we'll finally be able to. Let's just try building it first, and that will tell us whether there are any cases that we've missed. The layout map is not defined. Yeah, okay. Where do we have this? In reference counting. Title layout. Okay. Any other errors? Incompatible pattern matches. So it's in reference counting. Is that it? Yeah, it has a layout. Any other errors? Oh, there aren't anymore. I think now we should build. And if we don't have any warnings or errors, what we'll do is move on to testing. And if we like doing that today, we'll do that tomorrow. And I'm not sure whether it's really whether it will turn out to be worth it to try this out. It would probably have been faster to just convert the program by hand instead of adding an extra feature to the language. But I wanted to do this. This was a good idea. This was a good moment to improve the language, so I took it. This is how Spiral got to this point where it is currently. I developed it according to need. Let me close the other tabs. I'm going to close this. And what's going on here? What's this layers text? Oh yeah, I think I accidentally ran the layers file, and it it ended up printing this but I don't remember putting in tests for the layers. I mean, Kosovo right line. I shouldn't be outputting that into a file. Yeah, why are these getting printed into a file? So yeah, I put these statements in here, and this redirects the I/O into this. I completely forgot about it. Okay, it's amazing that I'm running this for the first time. Okay, okay. Let me put in a message doing. We'll put stack mutable layout types into the language. Done implementing them. We'll test them out tomorrow. We're going to commit this here. We're also going to, yeah, of course we need to also commit it here. I forgot to do that. And I think I'm going to stop here for the day. And we're going to do the testing tomorrow. Hope you found this a little bit informative, maybe on how working on a language looks like. We started the day off by testing a few ideas out, and then we moved to working on this. See you soon. I'm so damn tired right now. Today I'm going to take it easy, but until then, let's just focus on uh, testing out the features that we implemented yesterday. Maybe I'll stop earlier for the day today. First of all, I made a mistake yesterday, and it was a serious one, so it's very easily fixed. If you go into the matrix multiply, take a look at this outer loop, you'll see that, this outer loop, you'll see that it's a projective loop. And for the machine learning library, we are expecting it to be a linear loop. We want every block to operate on all the inputs. So doing this will actually slow down the matrix multiply, and now I'm a bit afraid of what we'll get once we test the performance again. Basically, that benchmarking that we did yesterday is invalid. We have to do it again. I guess it's loading all the reports one by one. Okay, let's give this a shot. We're just going to run this a few times to see what the duration is, and after that we're going to test out the new feature, which are stack mutable layout types. I had an idea that maybe we could use them to replace references entirely, but that wouldn't work. They're simply, they're not the same thing at all. Oh, for fuck's sake. I think the memory throughput is it up? Yeah, I think it's up a little. No, not this. This is the matrix multiply. Yeah, but the duration has been wrecked. But all the improvements that I thought we'd get from implementing the new matrix multiply have been pretty much eliminated. We spent a bunch of effort trying to express the matrix multiply better, but it doesn't seem like it will affect the training performance at all. I guess the kernel is bottlenecked by all the other things that are going on. Yeah, it's basically 80. So yeah, it's for some reason there is no improved performance anymore. What can you do? Oh really? Yeah. No, wait. I was looking at the wrong things. It's still 80. 83, 84, 81. This is 248. Now it's 244. Yeah, it's amazing that it's not using all the registers. We cannot do anything. Okay, these uncalled accesses are necessarily the ones in the matrix multiply, but they're due to. Oh wait, these ones are due to the matrix multiply because they're load for global. And these are the async load instructions. Oh, never mind that. Okay, we can. I think we can close all by this. Yeah, great. Now we should stop opening them or startup. And yeah, that's basically it. I guess. Yeah, we did need to try to improve the matrix multiplies just to make sure that they aren't doing stupid things with registers, which they were doing. But now we're all out of potential avenues for improvement. It should have improved the matrix multiply at least 2 times, but it doesn't seem like it's happening. And while we were testing the matrix multiply, we did note that, at least very briefly, that on smaller matrices, like the ones that we are using here, it's getting a lot worse performance. Like on 8K by 4K matrices is getting 50% utilization, but on smaller matrices is getting like 35 or something. So who knows? Maybe on smaller matrices there are some other ways of implementing the matrix multiply, so it could get better performance. But right now there isn't anything we can do to improve the matrix multiply performance. At least I cannot, because I'm simply lacking the relevant knowledge on how to really go beyond the obvious. I think for to actually implement this matrix multiply kernel, I need to have the knowledge that only dedicated NVIDIA engineers possess, because I think I have been pretty much using everything that is public effectively, and what I'm missing are the hidden tricks. And it's very hard to really discover those. If I really wanted to, I should be studying the Cutlass library in depth and reverse engineering it and so on. But as I said, I don't feel like doing that right now because there are other things that I need to be doing. Maybe once we're training the agents in the background, we'll be able to dedicate time to that. But rather than even studying that library, it would be a better idea to simply try to get our hands on the Hopper cards, because they have dedicated matrix multiplication functionality that will make this task a lot easier. Yeah, I mean, it's very hard to be happy about this state of affairs. The duration is still 80. I'm not sure whether what we're doing with the stack mutable layer types will give much of an improvement. But I mean, let's give it a try. I don't have any ideas for how to particularly improve the performance of the kernel. Improving the matrix multiply was kind of on the top of the list, and it didn't really do anything. And this thing might give a tiny improvement. I mean, the stack mutable types might give a tiny improvement to performance, and after that, basically, I'll be spent. I don't have any ways of writing the actual game better. There is nothing superfluous in it. We basically done as good of a job as we possibly could. Okay. So let's just go forward. Now, if you look in the sphere models, where did I put that, that foo function? Uh, foo, uh, uh, mute. Okay, where did I do the thing from yesterday? Oh yeah, in performance. Did I maybe put it here? Oh yeah. This is what I meant. It's in performance. So let's close this. Let's open the VS Code plugin. Let's also open the Spiral language. I don't think I published this project yet. Right now I'm looking at the target framework and I'm wondering whether .NET 9 came out. I don't really pay much attention to the .NET development, and every time I look, it seems like a new version is out. Uh, everything .NET SDK. It's still .NET 8. It released on August 15th. I guess some new minor versions came out. Okay, let's run this. And now, because of the changes to the time imperator, we should be getting that this variable needs to be fully annotated. Really? Alright. I mean, by the time it gets here, it actually is fully annotated. So, okay, let's try this. QA. Layer type being set must be annotated. Oh yes. Mute int. We could do it like this. Oh, I see. So yeah, it could be it knows that it's a mutable type. And suppose we put in maybe a stack mute. Stack mute. Yeah, now that works as well. At least in the top-down stage. Since we have these stack mutable types, we have to actually make the constructors. I think that's in base. I mean in core, or rather in real core. Mute. Maybe it's in real core. I don't know. Oh yeah. Here it is. Here's the mute layout to heap mutable. There's also layout to heap. This is the unboxing. Stack Mutable. Stack mute. Oh yeah. I mean stack mutable. Yeah, okay. This should be mute. Stack mute. Okay, and this. I mean, we could make this the operator, whatever. Stacking it to the. Okay, so that's. Yeah, now I can construct these things. So arguably, at least this first time around, we should be testing them in the other core library, in the other folder. Well, let's just close this. We're going to go into this folder. We're going to make a new test. We're going to get rid of this. Wait, what did I do? Here it is. Okay, we should just. We're just going to paste. Oh, damn it. Okay, let's go. Let's see whether we can run the ML library like this, and we need to go into the core. We're just going to copy paste this into the other project. And equally, now that we have we've implemented the so that automatic port scanning. So now it can launch multiple instances of the Spiral language server. Like that one is on port 80, this one is at port, 8001. And the other is at 8000. Okay, so we have this. Now we can try out the stack mutables. For this one, we're going to need the CUDA backend. Spiral, it's already on this. Us. And I think, okay, inal join backend CUDA. Okay, now we'll do inal x equals. Okay, let's do stack mutable true. And let's recompile this. The fact that it's putting like this library here is very annoying. We cannot really run this right now, unfortunately. Yeah, we're going to have to do the test in the ML library because this is pretty useless right now. Oh yeah, we forgot the semicolon here. And that's pretty much the only thing I can really tell from this. Yeah, we also need to do to maybe do the indexing. Let's also try that out. X equals true, y equals I32. And then we'll try indexing into x, y. I guess we'll index into both of these. Oh yeah, this is nice. Let's also see whether setting this would work, like x. Let's make it false. If we build this, what's going on? Expected R record. And this is a compiler error. That means that this is a problem on the for the language, not for the user. So setting the stuff here doesn't work, and this is a problem in partial evaluation, I think, or the code generator. We're going to figure that out right now. Let's see. Expected a record. I guess not. So it's probably a problem in the CUDA code generator. Tile layout mutable set. Oh, I see. This is mutd. So here is getting the data, but what we've done yesterday is changed this type that we're passing into mute. So it's returning the wrong thing here, and if we go into mute, yeah, it's getting into this and then this. Let's see what's happening like inside in layout. Enrow type to data. Okay, that's not good. We're going to have to do. Okay, let's do this. Match x with. And this is going to be y. I think. Yeah, this is going to be y layout. X and. Yeah, we basically have to extract the type from this y layout here, and this should be done in this layout, and we're going to have to do that for pretty much. I mean, we're going to have to do that in every code generator. Raise code generator x compiler error expected layout type. Yeah, like that. I'm actually surprisingly fast at figuring out these kinds of errors. Like, it just comes to me, it seems. Okay, let layout. Okay, let's do this. Cogent CUDA, this cogent C. And I'm going to pause here and simply fill out these cases in the other two code generators, and then we're going to rebuild this again. Also, before that, into layout and yeah, actually no, not here, but stack mute. And yeah, and, we're just going to put a semicolon here, and that will fix that other error. Now let me pause. Okay, I filled out all the cases. I've been doing some other things. Never mind this. Let's publish it. Just trust me when I say that I filled out the cases. And okay, now we're publishing this, and it's complaining about the files being locked. Okay, let's close this. We're also going to close this. Now we're going, yeah, now we have to publish it into the compiler folder, not on the VS Code Marketplace. What I'm doing in the background is installing Cyberpunk, and it's kind of calculating the MD5 hash, and it's taking a ton of time. At this rate, it will take me literally hours to install this game, but right now I'm busy with work, so it doesn't matter. Thankfully, I managed to fit it in. Let's see. I may have to stop that once we start doing performance testing. I was kind of wondering whether some of the stuff that we did would break the other code, and I'm pretty sure that the stuff that we did to the mutable types would pretty much break all existing code. Thankfully, the mutable set. Thankfully, we fixed that right now. Now let's build the file, and we're still getting some kind of error. Expected layout type. What does it mean? Uh, what? So this error can only be like this. So it's in the setter, I think. But why is it showing up here? Like the last time it did show up in the right place. Okay, let's change these error messages. This is crazy. I mean, what is it getting here? Got. Okay, let's put in this and then got and then what? I guess show tie and x. And we're just going to do that everywhere. Control V, Control X, Control C, Control V, Control X, Control C, and we don't have anything anymore, I think. So okay, let's build this again. Let's first close this. Oh yeah, I guess we're. So is it getting this error while it's actually trying to construct the layout type? Uh, that could simply be it. Yeah, because that function isn't triggered only on the mutable set, but also on whenever the type is accessed at all. So we're going to have to check out not just the mutable set, but whether it's stripping the type anywhere else in the partial evaluator. Okay, let's build this. Build file. Got bool y. Yeah. It's basically just getting the type of the stuff, the thing that's inside it, and we have to fix that. So uh, let's go into the partial evaluator. Oh, y layout. I mean, I guess we'll tile layout index all index by key mutable set, and it's also a to layout. Okay, so it's I'm going to put a bookmark here. We have to check out the all of these. I don't think the problem is in indexing. Maybe the problem is in tool layout. Uh, okay, let me think. X style layout. I mean, the problem could also be in the code generator. So this is data to tie. Yeah, but this is what it should be. Yeah, this is fine. Okay, I see. So let's just check out how this title layout is being handled. Uh, yeah, this is so it's like this. So it's kind of mm, yeah, okay, I get it. Hmm. I mean, the easiest way that we could fix this is to just put the layout in. Where did it go in? Is to just put the layout inside of here, inside of the tie. That way. Okay, well, yeah. Now this is broken, and what we'll just do is let's make this the tie, not enable, but let tie equals and let's rename this to return tie. Okay, now that's done. And what we have to do is pretty much change all of this, like by layout. But actually, let's do y layout, and this is going to be and b, something like this. And in fact, what we're going to do is factor this out. Match B with yeah, we're simply going to do while layout here. We're going to put this in here. Heap mutable. Oh, whoops. This should be like this. Oh, yeah, not bad. And of course, now we have that issue of we could be passing an error type here, so we have to do a compiler error, compiler error, expected layout. I guess this is the cleanest way of doing it. Even though we have to do a bunch of extra type checking in the code generator. Yeah, in the past I was pretty anal about trying to fit as much as possible into the AST, but it's actually pretty beneficial to just reuse it and maybe just put some print statements instead. Oh yeah. Instead of doing it like this, layout, we should do just match layout with. And we're just going to fold this in. And in the future, this is going to be really helpful because if we add another layout type, we're going to get inexhaustiveness warnings. But the way it's currently is done correctly, it would be caught. It would instead be buried by this wildcard case. So that's why I want to factor it out like this. Oh yes, no, yeah, this is good. Now, as you can see, if we added another layout type here, we'd get an warning at compile time that the patch matching cases are not exhaustive. We are going to have to. Let's see, do we have any other errors? What's this? Align layout, heap mutable. Why are we getting this warning? Do layout. Oh yeah. I forgot to remove this. Yeah, good. And I'm going to have to do all of this in all the other cases as well. So let me pause here and I'll fill those in on my own. Okay, well, I think I did all of this. Now we can try publishing it again. I'm kind of getting distracted with the Cyberpunk installation in the background, but it should be done before long. Okay, let's close this. Now we'll try publishing it. I changed it quite a bit, so I think we're going to have to add some tests for all of the backends, whether... oh, I missed something. Yeah, but as I was saying, we're going to have to add some tests for all of the backends. to make sure that they still work. Let's see. In fact, I think I do have the tests for layout types in what in the compiler tests folder. I'm just not sure which which test it is. I will just do a check for layout in that folder. I mean, do a search for a layout. Okay, so it built it. Now we can run this. Let's see if it still works. It doesn't. Compiler error, expected a layout type, but it got this shit. Wait, did it publish it? Really? And it's still giving us the same error. Let me erase the table. Oh, now it's a destruction git. Oh, I see. It happens in layout index as well. Yeah, I guess we're going to have to change those parts too. Ah, crap. Okay. So you can see what the problem is here. Instead of this A, it needs to be. It needs to pass in the entire layout type. Okay, I'm going to have to pause here and I'm going to fix this in all the other cases. Be right back. Okay, done. This feature ended up being a lot more work than I had anticipated. I hopefully will at least get a few milliseconds of improvement out of it, but who knows. I mean, if it doesn't give an improvement, we'll still keep it in, because who knows, maybe it will be useful in some other situations in the future. It's not a bad feature by any means. Okay, now let's publish it. Publish. Close this. Oh, this thing is still installing. It's still building. It will take a while. I mean, it's really taking a while. That's the grammatically correct way of saying it. Let's see. Why is it not? Oh, what the fuck? What the hell? Oh, wait, what? Wait, it's telling me this is some kind of PowerShell bug. What the hell? Okay, this doesn't have anything to do with Spiral. It's like something weird happened to PowerShell. This never happened before. Okay, let's try building it. Build. And it really did build now. Okay, now It's creating it, it's indexing it, and it's setting it. Yeah, perfect. Uh, now what we have to do, this test is good. Now we just need to check out whether the other mutable layout types still work. I mean, whether the other layout types work in the other backends. Does the stack mute work? Let's close all of these. Close, close, close. I guess we're going to just do a search in this folder if possible. Uh, um, layout. Layout type. Does indexing. Okay, this is one test. Test 54. This is array void types. Okay, I guess we have one test here. Okay, we're going to go through this with all the backends. Let's try starting in the Python one. If I run this, does it work? Okay, let's try. Let's also try the other backends. Why is it not keeping it open? Spiral. Let's try the F# one. Spiral build file. Are we getting some kind of error? Yeah, we're getting the same problem. I guess I forgot the layout type case somewhere. Just a second. I'm actually not sure what the problem here is. Like, this is where it's constructing the layout type. I mean, is it possible that the type here is wrong somehow? I mean, in that case, it should be wrong in the partial evaluator. Title layout, return type. No, it should be impossible. Why layout? Okay, let's try the C backend. I have no idea what's going on here. Build. Yeah, we get the same error for this one. But for some reason, for the Python backend, it works. That's very weird. Or maybe it doesn't even work for it. Maybe these are the results from last time. Build file. Yeah, in the Python backend it works, but over here it doesn't, and it's very confusing. So the F# and the C backends don't work. Okay, let me pause again. Okay, I get it. Uh, this is really weird. I mean, this work. This shouldn't be working, but it is when we tried it out. Wait, maybe it never really. Yeah, maybe never. We never tried out this pathway. Maybe that's simply the explanation. Okay. Let's see. Oh, do we not have? Um. Yeah, we should be destructuring on lay. Okay, we're going to much lay with. Oh my god, this is so much work. It's insane. I didn't think this the whole way through before I started implementing it. Let's see. Yeah, we have to refactor all this. Like, okay. I'm going to pause here and do this refactoring. Be right back. Yeah, I think this should be it. Oh yeah. The C backend. This is the share backend. This is the Python. Okay, no, not bad. We're going to let's try publishing this again. Be right back. Now let's see whether this finally works. There have been so many breaking changes this time around. Let's try running this. Yeah, I'm pretty confused why why this works in Python. Why this worked in Python in the Python backend. Whatever. Well, oh yeah, we need to test it in the F# backend. Okay, build file. Then we go here, and we'll see whether it works. I mean, now how do I run this? I guess Alt and Enter to send it into the F# interactive. Okay, yeah. It works perfectly. Nice. Now let's also try the C backend, and that one we need to compile. So I cannot even do that right now. We're going to have to use the online compiler. Expected a layout type. Oh my god, it's still not correct. Expected a layout type 7. Okay, let's check this out. What's going on? Uh, I mean, I can guess what the problem will be. I don't know. This has a bunch of extra stuff. As a It has a bunch of reference counting code which might be using the old style. I guess we'll just check out on the yeah, I guess this is the only thing. Okay, let's give it a try again. Pausing. Okay, let's finally try it out. Oh, wait, what did I do? Oh, it's building, and let's see. We have the C backend. And it's actually the same as before, it seems. Nothing's changing. Let's delete it. Let's compile it. And if you look into... Oh, for fuck's sake. If you look into the source control, we don't see any C files. So yeah, that's proof that it's the same as before. Okay, not bad. I also want to try... okay, let me just take a look at some of the neighboring tests. Maybe it's... Oh, here's the heap mutable type. Oh yeah, this is perfect. And also, we saw this, so we should also be indexing into it. Q. Yeah, like that. I'll modify the test so it's like this. And we'll run it. And this is exactly the test that I wanted. Build file. And yeah, this changed the C file. Let's see whether... Let's put this into online C compiler. And run. It exited without errors. Oh, really? Oh, it exited with errors, actually. Yeah, that was probably the reason why I was returning a 0 at the end. And then what? Wait, what was I indexing into? Just a sec. Oh yeah, V1. Yeah, no, not bad. Okay, so now let's try the other backends. We tried the C, let's try the F# one. And no errors are popping up, so it's most likely right. Okay, so we have that. Let's also try the Python backend. Python plus CUDA. Perfect. We also need to test this out in... We also need to test out the stack mutable types. Let's see. let's go here. And I mean, it works on the CUDA backend. We also need to test it whether it works on the Python side. Oh yeah. Actually, the Python doesn't support this type. I forgot about that, so we're fine. Okay, so I think we're good now. We know that all the backends function properly with all the layout types, with the stack, I mean, with the heap and with the heap mutable. And the stack mutable types are working properly in the Python backend. Done with basic testing. The work well, and the new we won't be pushing out a new minor version of the language just yet. We're still in the testing phase. Let's close this. We're going to close this. And let's see. Oh yeah, we're going to run the ML library. Oh yeah, in the type inferencer, we are checking that it's a stack mutable, right? Or a mutable stack mutable. Oh yeah, we're checking that they are these two. In fact, instead of doing it like that, yeah, I want to actually match play with the, and if it's one of these two, then fine. I want to future proof ourselves in case we end up putting another layout type here in the future. And if it's a heap, expected immutable layout, and this should be expected layout. Let's take a look. Expected. Maybe not. Maybe having the same error is fine on both sides. I mean, maybe having the same error on both sides is fine. And if we in the future add another layout type, we're going to get a warning that this pattern matching case is not exhaustive. And I hadn't really expected to add the stack mutable layout type either, so that's why I didn't ensure myself. So, okay, this feature is finally implemented. What we're going to do now is move on to the testing. I guess we're just going to put it into the... We're going to try out that performance, the performance module. We're going to try building it again. And after that, we're just going to substitute the mutable type with the stack mutable and see whether there's any difference in performance. Oh, now if this would only finish installing. Right now it's really taking the performance of my rig. It's taking twice as much time to compile than it does usually. Uh, I mean, it's amazing how long it's taking it to actually install. It really it's maybe taking a third or half of the time it took to download it. And I did download like 60 gigabytes. That's how large the game was. Okay, so yeah, now I have to run this. Did I publish it? Yes, I did. Okay, let's do it. Uh, Recently my hand has been hurting, so I haven't been playing games much. I've been just watching playthroughs on YouTube. And I've heard about the Cyberpunk game for a long time. And I've been reading that they finally got rid of the bugs, so I wanted to try it out. These days, you have to wait for a game to release and then wait another few years after that, for all the bugs to be fixed. I mean, this game got released like 4 years ago, and they're still working on it. Amazing. Okay, what the hell is this? Oh yeah. I'm just reminding myself that we need to add noise to the exploration. Okay, never mind that. Here we have this performance thing. Performance. And first let's pick the right backend spiral. Oh yeah, it's already picked. Now we'll build the file. Is the compiler maybe crashing? It isn't. And we built a new file here. Let me just try running it. This is just to make sure that everything still works. It's going to be compiling it. And after that, what we're going to do is replace this mute with a stack mute. Let's see, which mute am I talking about? No, not this one. This is just to test out type checking. What I'm looking for is where is it? The game state. Oh yeah, here it is. Stack mute. And we're also going to replace this with a stack mute. And now we'll just build it. Let's see, stack mute. Wait, what? For a moment, yeah, I saw this, and this shouldn't be here. Mute 0. Stack mute. We should have this mute stacked. Why is that happening? Okay, it was only luck that I managed to spot this problem. But since I did spot it, we need to investigate it. So if you look at the types here, they're actually the same as for the stack mutable. And most likely we're calling a mute instead of stack mute somewhere. So let's go into this into the CUDA backend, and let's go stack mute. Are we maybe calling mute instead of stack mute somewhere? Here it is. Here's the stack mute. The problem is not here. Oh yeah. Here it is. Stack mute. Okay, let's publish this again. Now, if we compile this again, let's see, why is this thing not going away? The mute is still there. Wait, did I maybe run it too quickly? I don't know. This isn't right. I guess we have another place where we're calling mute instead of stack mute. We managed to find one place, but we need another. Okay, so let's investigate it. Let's go into the CUDA backend. Let's see where. Let's find all the references for mute. Heap mutable. This is mute. Heap mutable. This is mute. Heap mutable. This is This is mute. It's calling mute here. Oh damn. We probably have this error. I mean, no, we cannot have this error in the other places because they don't support the stack mutable type. But over here, we have to check whether the layout is. Okay, match t with file layout. Match play with heap and what I'm just going to do is this. Fun X. Okay, we're also going to have the stack mutable, stack mute. Oh wait. This is supposed to be mute, not heap. I mean, can we do this a bit better? This is ridiculous. I mean, we're matching it here, and we should be also destructuring it here. This is ridiculous. What do I do? over there. Okay, let's. I guess for now, let's just plow through this. Let's refactor this. Match my width. Yes. Okay. Like this. Okay, so I'm going to. Okay, let's do. Let A equals. This is just going to be the same as before, like mute what? T. Oh yeah, we need the T. This is going to be stack mute. I'm basically duplicating the error message. Okay, this should be fine. Now, we're going to try building this again. Oh yeah. Oh yeah, I need to close this. Once we actually get this to compile properly, I'm going to take a break until this finishes installing. And then we're going to do the testing in n-site compute after that. The reason, as I mentioned, that this installation is very computationally intensive and it's slowing down the rig too much. So we wouldn't get any useful data if we try the testing while this is being installed in the background. And it's taking a long while, so I cannot pause it or something like that. And I don't want to cancel it right now, only to take for it to take 2 hours to install again. So yeah, that built. Now let's try. I mean, the compiler built. Now we'll check out whether the program itself builds properly. We have the stack mute and mute here, and we want the mute to go away. Yeah, and it went away. Perfect. Yeah, now we don't have the mutable types anymore. Let's just try running this once to see if it compiles properly. Oh wait, the module doesn't have the key backup. Whatever, we got rid of that. Terminal. It seems like, yeah, we do have some issues here. Static array identifier v2 is undefined. We are not printing the types properly. We are putting these ampersands to the left of the type instead of to the right. We have to fix that. Hopefully, once we do, this will be the final error. Quadrant CUDA. Let's see, where's the type V? Do we have a type V anywhere? I need to close this, and I'm going to pause here because it takes a while for it to compile. Be right back. Okay, here it is. Now you can see that this ampersand is to the right. Now let's try running this, and hopefully this time it runs to completion. I pressed... oh wait, I was on the wrong keyboard layer, never mind. Okay. Yeah, it finally ran. And this thing... I don't want it to open this. I don't want it to launch this. I mean, didn't it install this already? Okay. God damn it! I did this manually before I started installing it, and now it's doing it again. Okay, never mind. I guess we're done here for the morning session. I'm going to finish installing this game and the updates for it, and after that, I'm going to stop here for breakfast, and when we get back, we're going to try out this optimization. See you soon. Bye bye. Okay, the Cyberpunk game has finally installed, and we can move on to the performance testing instead. Let's do it. Let's run this a few times, and then we are done. I cannot be bothered to care about this anymore. So this is this is 22. Come on, load it. Okay, everything that has... Okay, this is not the kernel that we're testing. This is 254. Okay, what did we... Yeah, this is what we got once we changed the matrix multiplication kernel, so it actually does the right thing, which is use a single block to compute all the inputs. So we're getting 83, 84, 81, 85. Now let's try running this again. We ran it a few times. Oof. But this is a massive improvement. 50 milliseconds. Oh, okay, wow. This is. I thought what I honestly expected is that there will be no noticeable change at all, but this is a huge improvement. It even uses the same number of registers. Uh, yeah, this is. Let me just read it here. It's 85 milliseconds. Over here it's 51 milliseconds. Wow, let's try running it a few more times. I never expected this. I honestly thought that this would improve it by something like a few milliseconds at most. Maybe it could even make it worse, for all I knew. Okay, in hindsight, we made a very good choice in implementing this latest feature. This is 55. Previously it was 51. Okay. Oh, 54. Okay, one more time. $53. Oh yeah, great. We're going to stop here for this video. In the end, it turns out it wasn't really the matrix multiplication itself, or I think this optimization itself, that really gave us a huge boost, but both of them together. By reducing the number of registers that matrix multiplication is using, and then that allowed this particular optimization to really shine through. Yeah, this is a significant improvement. We nearly managed to. Okay, we didn't double it, but we did manage to increase the performance of this by 70%, something like that. Okay, well, let's calculate it. We will. Off the cuff, this is like. Excuse me. This is like 80. Divided by, let's say 52, whatever. So yeah, we basically split it up by 53%, 50%. Let's say it's 50%. So yeah, this was well worth it in the end. I'm really happy that I can conclude this video on this note, because we did manage to accomplish our goal, which is to speed things up. And yeah, I haven't been sleeping well. My hand hurts, and I need to think about what we're going to do next. Most likely, what we're going to do next is. I think we'll either get the CPR training to work on no limit hold'em, or we are going to implement the cross entropy method and train the neural networks using that. We'll move on to one of those things. We'll probably make it run on no limit hold'em. I've been really waiting to get a good agent for that game forever, so I'm looking forward to that. We also need to integrate this optimized performance implementation into the training loop. Where is it? Yeah, into this. But I think I'm just going to leave that for myself. You guys don't have to bother yourselves with that. So I'm kind of wondering, where is it actually? It's training this thing. Aha, so it's only training it in one position. Never mind. Uh, it's training computer against the computer. Oh yeah, I forgot about that. And over here in performance is training one agent against the random, and then against the other. Okay. This is the random training. So okay. I'm just starting to ramble right now. What I wanted to say is that I'm going to take the improvements that we did here and put it into the training loop myself. And yeah, please like, subscribe. It I guess it tells the algorithm that this content is good, and it's pretty unique content. So give me all the support that you can get. Also, give me more compliments. I like those. See you soon.